Welcome to our tutorial entitled Roadmap to Free Space Optics for IWCMC 2020. Obviously, we would have liked to meet you face to face, but given the situation, we are going to go with this virtual presentation of our tutorial. This tutorial involves four speakers, Dr. Abdurrahman Trishili from KAUST. Then we have Professor Mitchell Cox from University of Witwatersrand in South Africa. Then we have my colleague, Professor Boon Oy at KAUST, and myself, Mohammed Slimalwini. So each one of us will give you a part of this tutorial, which, by the way, has been submitted as a review paper in JOSA B, Journal of Optical Society of America. We will be happy to share with you the draft of our paper at the end of this tutorial. It will be part of the list of papers, but we'll be happy to give you a first draft of this tutorial paper on free space optics. So here's outline of the tutorial. I will start by giving you an overview, a high-level overview of of free space optical communication, giving you some background, some kind of big picture about free space optics, some of the challenges and opportunities, and let's say performance analysis kind of work that has been done over the recent years in the area of free space optical communication. I will then give the hand to Dr. Abdurrahman Trishili, who will focus on a new trend within free space optics regarding spatial mode multiplexing, including the kind of, let's say, emerging OAM-related research. So he'll be talking quite a bit about this interesting topic. Then we'll give the hand to Professor Mitch Cox, who will kind of follow up on Abdurrahman kind of part, talking about structural light, and in particular explaining how free space optics can be used to create this kind of, let's say, fiber optic over-the-air network, in particular in areas suffering from the digital divide, in particular Africa, as you know, is a place where this is a big problem. And in South Africa, there has been some interesting studies on how to use free space optics to kind of substitute the fiber, and be talking quite a bit about that. And then at the end, the tutorial will be concluded by kind of an important aspect to all this. When we talk about free space optics, obviously, at the end of the day, we need to talk about hardware. This is contrary to classical RF-based wireless communication, where we take it for granted that we have, of course, antennas and RF devices. In free space optics, we are talking about optoelectronics, photonics kind of device, like lasers, LEDs, photodetectors, and so on. And that's why we have our colleague, Professor Boon Oy, who will be kind of giving you some updates on kind of essentially recent trends or recent progress in the area of hardware as they relate to free space optics. Then we'll have a wrap-up of the whole tutorial. Now, obviously, the whole motivation behind this work is that we are living in the so-called zettabyte era, or we are converging towards the zettabyte era. We have seen over the recent years this continuous increase in the number of subscribers, on the number of connected devices. And along that, of course, we are seeing much more data traffic flowing through the networks. And we see these two graphs increase in the number of connected devices and people. Actually, we don't have a picture for it, but you have probably seen it in some other presentations. And on the right, we see this kind of byproduct of that we are having like a tremendous increase in the amount of data that's being exchanged wirelessly. So this is kind of a snapshot what happened in 1 minute of internet, all kind of transaction that people all over the world are going through, starting Google, Facebook, and so on. And on the top of that, you are probably also aware of this kind of a new interesting kind of direction towards autonomy, or in particular autonomous connected cars, which will require also quite a bit of exchange of data to kind of make sure that these kind of autonomous systems are safe and secure. So you have all kind of devices within this car to be connected to the infrastructure, to other vehicles, to the network in general. And essentially, obviously, there is a lot of need to exchange and transfer data wirelessly. So this is not obviously new to us. We have seen this before. When I see we have seen this, I mean we have seen this kind of continuous pressure to improve performance. So if you look at the history of evolution of wireless generation systems, we moved from the 80s, where essentially we started talking about wireless communication with 1G system. These were very basic analog voice kind of systems. Then the 90s, we kind of witnessed the emergence of 2G GSM kind of systems, where essentially the big breakthrough at that time was to move from analog to digital voice. Towards the end of the 90s, we went from just voice communication to voice with kind of minimal data transmission capabilities via edge and GPRS. That was, the time where we start using SMS and even email in our cell phones. 2000 era was the time where essentially we start having mobile internet services in our phone. We were even able to use GPS and start having some positioning and localization capability as part of our phones. And then came 2010 era, where basically we start essentially enjoying mobile broadband transmission, including video streaming. So this is pretty much the time where we live in now. And now we are in end of 2019, early 2020 actually now, where basically we are seeing the deployment of 5G. So deployment of 5G being kind of witnessed worldwide with the three very famous user scenario: EMBB, enhanced mobile broadband, which is trying to go towards this super high data transfer capabilities; ultra reliable low latency communication; tactile internet kind of application; autonomous car driving application, where basically reliability is very important, but also low latency is critical. Again, kind of a key example that is often given for this user scenario is autonomous cars or remote surgeries, for instance. And then we have the third corner, or the third important user scenario, which is massive machine type communication, MMTC. This is the kind of paradigm where we see 1 million kind of device per kilometer square, or equivalently one device per meter square that is connected. This device can be a sensor or actuator, but the bottom line is we have this kind of extreme connectivity in terms of massive deployment of connected devices. These are the three famous user scenario around which 5G is built. And now, obviously, in 2020, as we start deploying 5G, it's the time to start brainstorming about 6G. As you notice from this initial slide here, it takes about 10 years to kind of develop a new generation of system and make it, kind of viable, and another 10 years to start deploying it, start using it, make it mature, and move on. And that has been our cycles, let's say, evolution over the last 5 decades or so. So obviously, this slide here is kind of illustrating exactly these three user scenario and the different metrics they are hitting. Obviously, every particular user scenario has particular requirement. EMBB will be after extreme data rates and extreme capacity. Mission critical and control is after ultra low latency and ultra high reliability, and massive Internet of Things or massive massive machine type communication is about ultra low energy, deep coverage, and ultra high densities. This is how 5G is evolving. And when we talk about 6G, obviously the natural thing we'll start with is that 6G is going to be a natural evolution of the previous generation of system. When we say natural evolution, we are talking about pushing the envelope even further, trying to go basically towards higher speed, lower latency, higher capacities. It can be a combination of these user scenarios. You may have kind of, let's say, for example, gaming application in the AR or VR type of scenarios, where basically we may end up using enhanced mobile broadband kind of capabilities combined with ultra reliable low latency capabilities. So basically we have these kind of real-time games that requires quite a bit of data transfers done also at very low latencies. So this is one aspect of 6G, and as I mentioned, this is the brainstorming time. Over the last 12 months, we have seen the surge of perspective, vision, kind of papers being submitted by different research groups worldwide. We had our share of this is speculation and brainstorming about 6G. We wrote our own paper, and it's published, or it was published in January 2020 in Nature Electronics. It is kind of listed here. And we gave our kind of perspective on how we can push the envelope as part of 6G. Now, obviously, when we talk about evolution of wireless communication systems, one of the, let's say, main constraint always that we have to keep in mind is spectrum. Spectrum is a natural resource. It is essentially regulated and optimized worldwide, and essentially this spectrum is allocated into different band because there are many competing applications such as radio and TV broadcasting, government, commercial service, all going after the spectrum. And obviously, when we talk about spectrum, often or kind of implicitly, we are kind of more kind of let's say implying that we are talking about the RF spectrum, but the spectrum is much wider than that. In particular, as you go towards extreme high frequencies, you move from RF spectrum to more the optical spectrum, and there is plenty of bandwidth available up there. And that's, in a way, one of the motivation behind what we are going to be talking about as part of this tutorial. So, in a way, when you look at the evolution of wireless cellular communication systems, you are essentially trying to maximize the so-called area traffic capacity. Some people call that area spectral efficiency, measured in bit per second per meter square. So if you multiply up and down by node and by hertz, you create these three factors: bit per second per hertz per node, known as spectral efficiency. Sorry. Okay, and then node per meter square, which is known as the network density, and then hertz, which is just the spectrum. So if you are living in this kind of world and you are trying to kind of get a 1,000-fold improvement, obviously you need to improve along these three directions. You need to improve along the spectral efficiency direction, along the network density dimension, and along the spectrum dimension. And this leads us to this next slide, where we kind of list some of the key technologies that are being pursued worldwide. So to improve spectral efficiency, there is a lot of work on massive MIMO, artificial radio space, or smart reconfigurable or reflecting surfaces. This is also quite trendy topic. Interference management, full duplex radio. All of these approaches are trying or are having as an objective improving the spectral efficiency of systems. Then we have obviously densification of the network, which is an important other direction, trying to reuse the spectrum more aggressively, more efficiently, with all kind of variant to that, spectrum sharing, small cell, heterogeneous networks, and so on. And then there is obviously the kind of third direction and third approach, which is to go for just more spectrum, either by aggregating the spectrum in the lower part of the spectrum, or going towards the extreme upper bandwidth, like millimeter wave, terahertz, and at the end, one can hit the optical part of the spectrum and start using it to essentially advocate for optical wireless communication, which is the main, again, topic of this tutorial. So if you want to summarize, this is what we call RF kind of part of the spectrum, and that's quite congested. This is where most of the work has been done, or this is where basically essentially most of the current and emerging, let's say, wireless communication system are operating. And the idea is to move towards optical part of the spectrum, which includes three-part: infrared, visible, and ultraviolet, and start using it basically for wireless communication purposes. So one of the first kind of interesting statement that we can make at this point is that the RF spectrum is licensed, is fully regulated. It's quite expensive to operate over the RF spectrum. We need all kind of rules to follow in terms of amount of interference you are allowed to emit, or like license that you need to kind of get from the government. Now, the optical part of the spectrum, at least so far, is unlicensed, and there's plenty of it. It's like very much availability in this part of the spectrum. There is up to about 30 terahertz of band available for use. So if you try to compare RF versus RF, so obviously the available spectrum is much higher. We have this kind of interesting observation that while RF spectrum is currently, has been and is going to probably always remain regulated. So you need a license to operate on the RF spectrum. The optical part of the spectrum is currently unlicensed. Equipment density, we tend to have a smaller component because we have smaller wavelength. So the hardware tend to be smaller and more compact. Power consumption tends to be lower, so we tend to be more energy efficient. We are able to achieve, given that we are dealing with smaller wavelength, much higher data rates. And because most of the optical wireless communication system tends to be kind of, especially in the free space optics topic, focused kind of laser beam kind of transmissions, we are talking about more secure kind of type of communications, where it's more difficult to intercept basically the communication, the broadcast type of communications being used in RF communication. So RF communication tends to be more susceptible to eavesdropping than let's say free space optic communication. So when we talk about optical wireless communication, there are three families of technologies that are being typically used. There is free space optics. This is what we'll be focusing on this tutorial. This is typically point-to-point, long-range communication systems. You are trying, for example, to cross this river. You don't want to kind of dig and put a fiber optic kind of cable, but that solution can be provided or by free space optics. It operates in the near infrared band between 700 nanometer all the way to 1600 nanometer. Now, if you go towards the visible light part of the spectrum, then you can use LEDs that are typically used for illumination, for communication. That's the concept of Li-Fi, light fidelity. It kind of piggyback on the fact that LEDs are there for illumination to start modulating the intensity of the let's say light being emitted from the LEDs, and embedding information in these kind of fast variation in light intensity that are kind of not visible, or not, people will not be able to perceive this very fast variation of light intensity, but essentially is sensitive photo detector on the top of your laptop or smartphone will be able to detect this variation and decode the information that has been encoded in these light variations. So that's the concept of Li-Fi. Also, there is something a little bit more futuristic, but quite interesting, which is ultraviolet communication. This tends to be interesting from the perspective that it allows essentially non-line of sight optical communication. When people talk about optical wireless communication, the kind of implicit assumption that we are talking about line of sight. You need to have kind of visibility or line of sight, let's say, between transmitter and receiver. This is true for free space optics. Obviously, it's true also for Li-Fi or visible light communication. That's not true for long line of sight ultraviolet. You know, you can kind of shoot a beam towards the kind of stratosphere, and in these bands, like the ultraviolet band, scattering happens, and the signal can reflect back and can be received at the other end, although we may have an obstacle like a hill or a building on the way. So that's kind of one of the advantages of UV, but obviously there are a lot of hardware challenges. There are a lot of kind of, maybe other issues one has to deal with before this becomes a reality, and that's obviously not the objective of today's tutorial. So tutorial of today is focusing mostly on the first aspect or the first family of technologies, which is about free space optics, high speed, point-to-point free space optics communication. So what are the kind of typical benefits? Again, when we talk about free space optics, we are talking about unlicensed and unbounded spectrum. It's cost effective. It can allow you to transmit quite a bit of data without having to dig. You can bypass all kind of digging rights below a river, or if you have a tunnel. So it kind of allow you to kind of basically very quickly install your fiber optic network over the air. It's narrow beam width, so it's energy efficient. It can be put on the top of a building, but actually it can be put behind windows. As you know, light can go through like a transparent window. It's quite relatively easy, let's say, to install and to put in place. It's a fast turnaround. Again, there is no need for digging and installing cables underground, and it's suitable for brownfield. What we mean by here is that obviously fiber optics, it's ideal when you start from scratch, when you have a green field, a new neighborhood, a new city being built. Then you can put as part of your plan to include fiber optics. But if you go into a territory or an area where already things are established, it's kind of more complex often to kind of after fact to dig and start putting a fiber optic network. That's one of the advantages of free space optics. You can establish again your free space, your kind of fiber optic over the air network by using free space optics. So the application, are quite interesting. Although it's not really a new technology, it has been there for many, many years, initially for military and space application. But now with the surge and with the need for more spectrum, we are talking about free space optic as a last mile solution. If essentially you have a new building coming to the town and you cannot basically again dig and connect it through a fiber optics, free space optic can be the way to connect that building. It can be an interesting backup solution or kind of complementary solution to a fiber optic network that can be kind of going over capacity, or can basically kind of fail at any point. So having another way to kind of connect routers and the networks, making the network interconnected is an interesting other concept to make the network more resilient, let's say. You have a temporary event like Olympic game, World Cup, a concert. You need a surge of capacity in a particular area for a short period of time. Like here we have the stadium. Again, there is no point to establish full infrastructure that is going to be available 24 hours for 7 days. You need just to have this for maybe a couple of hours, twice, maybe like a month or something like that. So the idea is to use a free space optics and to use that capacity during that event or during that period of time, Olympic Games, where that extra capacity is needed. Once that event is over, you can dismantle the network and take it somewhere else where capacity is needed. And of course, as we talk more and more about 5G and 6G and smaller cells, of course, cells needs access points or base stations. These base stations have to be interconnected or connect at least to some kind of backbone. And this connectivity was done traditionally through fiber optics, but when this thing grows, when you start having a lot of these small cells, obviously you want to go to a wireless backhaul solution or a wireless front haul solution. And if you want to have a backhaul that is wireless, but is a backhaul, which means it has or it needs a high capacity, then again, free space optics can come very handy as a perfect substitute for fiber optic high capacity kind of communication. So again, this is the kind of review tutorial paper we talked about, and we will make it available to the participant of this tutorial as a way to kind of have notes and a full document describing what we are talking about in this tutorial. So another interesting application of free space optics is in the area of data center communication or data center networks. So, I showed you earlier in this tutorial what happens in 1 minute of internet. Obviously, a lot of these kind of transactions are going through data centers. Data center is a collection of these racks. A rack is an ensemble of these, say, computers or essentially units that have some storage, some computation, and some communication capabilities. So all of these kind of units have to talk to each other. They have to talk maybe with similar units in other racks. So obviously it's a fully connected network that is needed. And the way that has been done, it was done through fiber optics. And that's obviously the way to go if you want to, let's say, connect all kind of racks. So it can be very complex if it's unstructured. You can do a better job and try to come up with a structure and even color code to connect all kind of racks and all kind of units between each other. But the idea here is to kind of gain in overall complexity and reduce the cost by going for a full wireless solution, to remove all of these fiber optics and to connect every single rack with a free space optic transceiver, and essentially allow to have a terabit per second exchange within these racks wirelessly. So there is an interesting kind of niche area for free space optics. We did work on this in collaboration with Professor Bassem Shihada, and we have few papers that are kind of listed here if you are interested to kind of study or get into this particular niche application of free space optics. Now, another interesting application or aspect where free space optics has an interesting kind of advantage is this problem of digital divide. So I was talking about 5G and 6G and how we want to push the envelope, but we tend to forget that actually we are in many parts of the world dealing with much more basic problems. If you look at this map, which show you the basically percentage of connectivity in the world, then you see that many of these, let's say, developing countries in Africa or Southeast Asia or even South America are either not connected, pretty much not connected if you are below 10% or so, or underconnected. By underconnected, we mean that, we probably have some kind of ways to communicate via voice or super low data rate for data communication, but you cannot enjoy the full benefit of the internet. And if you try to understand the reason behind this bad kind of statistics, obviously there are the very basic reasons due to, let's say, let's say social, educational background of a fraction of world population that is not kind of computer skilled and don't know how to use a phone or a smartphone, let's say, or a computer. But there are also other kind of very important economical and technical reasons. So when we say an economical reason, we say what we mean is obviously these kind of mobile network operator, or more generally this telecom industry, works on a return on investment kind of economical model, which means these MNOs kind of buy the spectrum quite expensively. They have to kind of invest in research and development, have very kind of skilled people that they have to again pay, and so on. All of this is done upfront, and at the end of the day, these MNOs, need to get back their return on investment, and the way they do it is by essentially installing their equipment, their base station, let's say, in highly dense urban environment. So it does not make much sense for a mobile network operator, to basically kind of dig hundred, if not thousands of kilometers to install fibers or even just simple cables to reach a sparsely populated remote or rural area, because this is not the way to get back your money, as simple as that. So this is of course what is well known as backhauling or connecting remote areas in a cost effective fashion as being one of the big barrier to kind of establish connectivity, or let's say or bring global connectivity. Of course, there are some other reasons, like, for example, the fact that we tend to forget that if you want to have an up and running communication network, you need to rely on essentially underlying power grid. So if the power grid is not there, or let's say if it's not reliable, obviously you cannot have a reliable communication networks. Now, bottom line, it's a problem that we are facing, and it's becoming more and more important problem. And the way you can solve this backhaul problem is by bringing aerial or space connectivity. In other words, high altitude connectivity. So instead of going through cables, you go through HAPS, high altitude platform. Some people call them high altitude pseudo satellite. These are kind of mega or big drones. Some of them are of the size of a Boeing 737, but kind of much lighter. They are covered typically by, let's say, photovoltaic cells, because they need to capitalize on solar energy in order to keep flying for maybe 1 month or more. And they will be acting in a way as a flying base stations. So you see them here, kind of flying at 20 kilometers above the ground. There is this Aquila project that was a kind of a proof of concept that was done a few years ago. More recently, there has been this interesting Zephyr project, basically championed by Airbus. They all have the same concept. This is a Loon project of Google. We are talking about stratospheric communication, communication from 20 kilometers above the ground. Just for your information, just in case you forgot about it, planes typically fly at above 10 kilometers above the ground. So we are talking about twice the altitude, let's say, of airplanes. And they're acting as a flying base stations, and they provide connectivity to wide and covered areas. And you need many of them to kind of cover big and connected, big regions that are unconnected. Now, to interconnect these UAVs, to create this kind of network over the air, you need to rely on free space optics. So many of these inter UAV or even intersatellite communication link rely on free space optics. And actually, even one of these UAVs or HAPs, let's say, need to be connected to the ground, and this mother UAV may use free space optics to connect to an optical gateway station. So as I mentioned, there is Aquila, kind of by Facebook. There is also this Zephyr project from Airbus. There is the Loon project, which was essentially started under the umbrella of Google, but now it's a fully independent company operating under Alphabet, and actually getting some interesting, let's say, initial or providing some interesting initial connectivity solution to places like in Peru or in Kenya. And another kind of interesting application of free space optics is in the context of space communication is very high throughput satellites. So this is the next generation satellites that is expected to be deployed by 2030. These satellites have two sides. There is what we call the user side. This is kind of RF beams that are adjustables and that are kind of tracking traffic on the ground, so they can kind of move towards where traffic is needed in remote areas, in air for airplanes, in the ocean for ships, and so on and so forth. And all of these beams are kind of backhauled through this satellites, and obviously you need a feeder link. Traditionally, very high throughput satellites, at least the current ones, are using the Ka band, but it's expected by 2030 that we'll be running out of Ka band spectrum, and actually we prefer to use that Ka band for maybe the user link. And what's being proposed, what's being studied in places like the NICT in Japan or DLR in Germany, the idea is to use as a feeder link essentially free space optics to be able to achieve this kind of super high capacity or super high speed, going all the way to 1 terabit per second of capacity or feeder link. Obviously, there are a lot of challenges like tracking, alignment, having to deal with essentially kind of cloud blockage, and how essentially you need to have some site diversity to be able to basically kind of reconnect with another optical gateway station in case the one you are currently connected to is subject to a cloud kind of obstruction. So these are some of the interesting kind of problems that one has to deal with when he or she looks at free space optics in the context of this extra niche application in the context of very high throughput satellites. Now, people are talking also in the context of 6G, in the context of connecting, let's say, suburban areas or low-income urban areas with this concept of integrated backhaul access or wireless mesh networks, where basically you have kind of access points that are interconnected in a meshed network, in a multi-hop, so information can kind of propagate in a multi-hop fashion, and to create this kind of let's say high capacity interconnection between these different nodes. You may want to rely on millimeter wave or on FSO links, or basically on hybrid FSO RF links. You'll see why this is useful when we talk about some of the challenges of FSO. And so that's another interesting application where FSO is actually quite useful. Now, obviously, when we talk about connecting the unconnected or this digital divide problem, we are also, as a byproduct, talking about emergency connectivity. So, like when you have, like we are experiencing now, pandemic situations, you may have people ending up being in area where they were not supposed to be, like living more in dense, in let's say in rural, in residential areas and working from homes. So there is a surge of capacity that is needed during day hour, like the day, the some hours of the day that they were not kind of. I mean, these capacity needs were not there in usual time. So one has to provide this extra capacity in this particular neighborhood, and when you have emergency connectivity, also because of like an earthquake or something like that. So basically, any kind of solution that we have developed for like connecting remote areas can be actually come very handy in the context of emergency connectivities. One extra niche application where free space optics is useful is underwater communication. Obviously, when we communicate underwater, traditionally we use acoustical waves. That's kind of the most, let's say, reliable and mature technology for underwater communication. This maturity, well-established kind of advantage comes with at a cost. The cost is that essentially we are dealing with a very low data rates, sometimes in the order of kilobits. If you want to go to something much more, let's say, um, suitable for video streaming, let's say, kind of applications, then obviously you need to go for some other kind of solution. And it turns out that communicating in the optical range, in particular using green or blue, depending on the turbidity of the water, so blue or green color or lasers or LEDs can provide this kind of high-speed capability that we are looking for. So again, that's one extra niche application where free space optics is quite interesting. So let us now move to kind of the next part of the tutorial. So let's see. So far, what we talked about is, you know, the kind of main kind of motivation behind free space optics in the kind of standard world of cellular communication, and then how actually beyond that it can be used for other niche application like wireless data centers, underwater, space, aerial connectivity for like UAVs and things like that. So let us now go back to some kind of technical matters and talk in particular about free space optics in terrestrial networks and see some of the challenges and some of the issues that we have to deal with. So obviously, as you propagate in the atmosphere, there are some essentially preferred bands over which you propagate, bands over which attenuation is minimal. And this windows happens to be around 850 nanometer, 1300 nanometer, and 1550 nanometer. Now, the good news is that essentially these match quite well what we are used to operate over in the optical fiber communication domain, which means that photonic devices have been built, tested, they have matured for this kind of application, can be reused for free space optics, and that's great from a cost efficient from a cost perspective. Now, although these are three interesting windows, it turns out that 1550 is the most interesting one these days, and the reason is that below 1400 nanometers, you may have essentially to deal with eye safety issues, which means you may have limitation on the amount of power you can use out of your laser. If you are operating above 1400 nanometers, you may have less kind of restriction in the amount of power that you can transmit, and that's why this makes the 1550 nanometer a perfect kind of wavelength or window over which you may want to operate. When we talk about free space optics, we have two ways of detecting the signal. Like in RF, you can use coherent kind of detection, or let's say a non-coherent intensity modulation direct detection. Obviously, intensity modulation direct detection is much less complex. It does not require any kind of phase estimation, but of course it provides lower kind of performance. Now, on the other hand, coherent modulation requires phase estimation, requires adaptive control to essentially perfectly or nearly perfectly estimate the carrier phase, so it comes at a certain cost, a complexity cost, but basically it gives you a better performance capabilities if implemented perfectly or near perfectly. So some of the challenges that the free space optics have to deal with when free space optics is deployed on the ground, you have to deal with all kind of weather kind of issues: fog, rain, snow, sandstorms. These are some of the issues that essentially can harm your communication links. In particular, fog is a killer. and sandstorm, at least in our part of the world. So many papers have been written on the impact of fog. We wrote ourselves few papers on the impact of sandstorm on the basically performance of free space optics links, and that can be a major problem for the reliability of these systems. Now, often one way to kind of bypass this problem is to use hybrid system that have a kind of a backup link, like let's say an RF backup link that will allow you to switch towards this RF link if your FSO link fails for a reason or another, in particular if these reasons are weather related reasons. Now, of course, one important other problem is alignment. Now, of course, free space optics offer you the super high capacity of multi-gigabit all the way to terabit per second, but this is under the assumption that transmitter and receiver are perfectly aligned. Now, in real world, you may have to deal with the micro vibration, weak earthquakes, dynamic wind loads, thermal expansion between day and night, that results in essentially some kind of vibrations, including, of course, like building sway phenomena. And these kind of vibrations can lead to misalignment between transmitter and receiver, and this misalignment can imply a certain reduction in the, let's say, signal to noise ratio, and of course, a certain degradation in your probability of error. Now, we have worked on this problem for many years. We characterize this kind of misalignment via what we call the XI parameter. The XI parameter is the ratio between the equivalent beam radius and the pointing error jitter. So we assume that we have vibrations. These vibrations are modeled as a random variable, and basically that's what we call the jitter. So it has a certain, let's say, a variance. If this kind of variance is very small compared to the beam radius, which means that the Xi is very high because the ratio between the beam is very and this this kind of jitter is very big. So if Xi is very big, basically it is like we don't have pointing error. On the other hand, if this variance of the jitter is of the same order of magnitude as the beam radius, which means C is anywhere between 0 and say in 5 or 7, then you have strong pointing errors, and this can lead to a strong degradation in your performance. So this is completely captured in a mathematical model that was proposed a few years ago by Farid and Halimovic, and it has been used since then. So now, if you want to go back to what I was talking about, if you want to quantify the different issues that you need to take into account in your budgeting calculation, you need to account for raindrop or snow, fog, smog. These are kind of more the kind of deterministic effects that you may encounter. There are some models that have been proposed. Of course, typical kind of attenuation we deal with. For rain, it can be depending on the rain rate between 1 to 10 dB per kilometer. Snow, it can be higher than that. Mist, it can be some 12 dB per kilometer. But as you see, fog can be kind of a killer because essentially it can completely kill your signal. So now, another interesting kind of problem, interesting at least from a performance analysis perspective, but of course it's really not interesting at all from the implementation perspective of FSO, because it can degrade the performance of FSO system quite a bit, is what is known as atmospheric turbulence or scintillation. So basically, because of this variation of temperature in the different layer of atmosphere, as essentially an optical wave propagates in the atmosphere, it may essentially go to these kind of turbulences, and the end result is at the receiver end, you may see or observe these kind of signal fluctuation or scintillation. This is quantified or like characterized, if you will, quantified, if you will, by the so-called scintillation index, which is a normalized mean. Sorry, a normalized variance rather. So it's essentially like variance divided by the mean squared. It's written in this expression. So it's the second moment of the irradiance, which is the power at the receiver end, divided by the first moment squared minus 1. It's equivalent of saying the variance divided by the mean square. So, I mean, the bigger is the scintillation index, means that the bigger is the variance compared to the mean, which means the bigger are the fluctuation compared to the average, and the more kind of turbulence you have, and typically the more problems you have to deal with. The smaller is this kind of scintillation index, then the lower are the kind of problem that you have to deal with from a turbulence perspective. So we have done some studies. I mean, this is actually a very rich literature on trying to quantify the effect of turbulence and scintillation on the performance of system, accounting for different kind of environment, desert environment, coastal environment, foggy cities in Europe. We have done a few years ago, one of our former PhD students, now he's a professor, Professor Wael Haidari, did some experiment here in KAUST, and tried to look at the effect of humidity and temperature in the summer on the basically amount of turbulence and received power. And we kind of had a paper trying to look at how this temperature and weather condition impact the received signal. So if you want to look at mathematically, how do we model all this? So you have a source, you have a destination, you have a very simple actually mathematical equation linking the transmitted signal X to the received signal Y. So Y is equal to the transmitted signal X multiplied by eta, which is the optical to electric conversion coefficient, I, which is the fading channel of the FSO link, plus some noise in a certain kind of acceptable regime. This can be modeled by an additive white Gaussian noise. So that's kind of the model we use. Now, eta, so X is your transmitted signal. Eta is just a coefficient, 0.8, 0.7, depending on the technology you're using. N is this Gaussian noise. Now, I is this kind of channel fading or channel turbulence coefficients. There are different models that have been proposed over time. So I can be modeled by a log normal distribution. This is good enough for a weak turbulence kind of condition where your scintillation index is small. It can be modeled by a negative exponential, like basically an exponential distribution. And that's acceptable if we have really to deal with super strong turbulence regime. This is not always the case. So as a way to bridge these two extremes between weak turbulence and very strong turbulence, one can use a very handy gamma-gamma distribution, which spans the range from essentially an exponential distribution all the way to some kind of log normal or gamma type model. And then if you want to get a little bit more, let's say, degrees of freedom, you may want to go with the double gamma distribution or double gamma distribution or Malaga distribution, which are more generalized models that can offer more parameter and in a way more degree of freedom to fit the turbulence data. So let us kind of focus on one of the classical models, the gamma-gamma model. So it's known as gamma-gamma because basically what it is, it's coming from the product of two gamma. Because actually when you look closely to the turbulence phenomena, it's due to two levels of turbulence, small-scale turbulence and large-scale turbulence. This is similar to the fading we deal with in the context of wireless communication, where we have microscopic kind of fading plus macroscopic shadowing. So in a way, mathematically speaking, we do have to deal with the same kind of problems where we have two levels of fading or turbulence. And IX is a small scale turbulence, it's modeled by a gamma distribution, and IY is a large scale turbulence modeled by a gamma distribution. You multiply them together you end up with this so-called gamma-gamma distribution. When you multiply two gamma random variable, you end up with this gamma-gamma random variable. Turns out that you can end up with things in closed form. The distribution for gamma-gamma distribution is given by this expression. It's function of the modified Bessel function of the second kind, the K function, and by the parameter alpha and beta, which are the parameter of the gamma distributions, and they are related to basically the Ritnov variance sigma r via these expressions. So sigma r is linked to this Ritnov variance to basically the wave number K, to the distance of the link, I mean the distance between transmitter and receiver, and to the so-called refractive index structure parameter. This Cn squared depends on the amount of turbulence in your channel. So obviously, the longer is your path, and the more turbulence you have within this path, the higher sigma r, and essentially the more turbulent is the environment you are operating over, which means the higher is your scintillation index. So typically, when sigma r is, let's say, smaller than 1 or much smaller than 1, we are operating in a so-called weak turbulence regime. When sigma r is roughly equal to 1, we are talking about a moderate turbulence regime. When sigma r is much bigger than 1, then we are operating in a strong turbulence regime. So these are typical curves that are shown in many papers, where basically you pick the parameter sigma r as small, you end up with like 0.2. Your alpha and beta parameter in the gamma-gamma model tends to be in the order of 11 and 10, and then you end up with this kind of green curve, which, the bad part of the curve is the lower tail. This is when the irradiance is very small. Basically, you don't get a good signal. So basically, you see here the green curve, this tail is very low, and that's kind of a weak turbulence regime. Now, when you go from sigma r 0.2 to 1.6, alpha and beta drops to 4.1 and 9.1, and then basically you move from green to blue, and you tend to go more toward the left. This lower tail becomes higher, which is not good from a signal perspective, because as you remember, I multiplies X. So if you multiply X, the transmitted signal, by a small number, we are essentially kind of destroying or killing your signal, and that kind of affect your reliability of detecting properly your signal X at the receiver end. And then if you move even further from 1.6 to something like 3.5, like strong kind of turbulence regime, alpha and beta go lower to 4.2 and 1.4, and then you move further towards the left by going towards this dashed red curve, and that's a strong turbulence regime. So that's the beauty of the gamma-gamma model. It allows you to move from this kind of red curve, like kind of more like an exponential kind of behavior, all the way to the green, which is more like a log normal or a gamma kind of behavior. So the gamma or the green is like the log normal, like weak turbulence. The red is kind of strong turbulence kind of regime. Now, actually, in one of our papers that are cited at the end of the tutorial here in the list of references, we're able to kind of develop a unified, let's say, expression for the probability density function of the end-to-end SNR of an FSO link subject to turbulence that is marked by gamma-gamma fading and pointing error. I talk much about the pointing error modeling. Suffice to say at this point that it is modeled through this Xi parameter. So as I told you, when Xi is small, then you have a lot of pointing. As Xi increase, then you are dealing with essentially no pointing. So this expression, which is function of the Meyer-G function, that's a special function that's available now in MATLAB Mathematica that basically you can program. This expression of the PDF is parameterized by alpha and beta. These are the kind of turbulence parameter, if you will. C is a pointing error parameter, and R is a parameter that kind of determine the kind of detection we are using. Something I forgot to mention, that the SNR obviously is depending on the type of detection. If it is coherent detection, then the SNR tends to be proportional to the irradiance. If it is IMDD or direct detection kind of communication system, then the SNR is proportional to I square. So basically, R can take 1 or 2, depending on the proportionality factor of I with respect to the SNR. And instead of trying to develop calculation for like IMDD and for coherent, we were able to kind of unify that in a single expression. And this PDF essentially is very handy in that context. Now, once you have this end-to-end SNR of an FSO link operating over turbulent channel and subject, let's say, to some pointing error, you can start, of course, as a special case, you can deduce all well-known distribution of SNR. So if you set R equal to, this is coherent case, X equal to goes to infinity, no basically pointing errors, you get this well-known Gapmeyer expression. When Xc is finite, you have a certain level of pointing errors, you get again this Gapmeyer expression. Now, on the other hand, if you get R equal 1, X equal 1, which is essentially coherent kind of detection, you end up with this kind of expression. And then R equal 1, finite C, you have this expression. So these are kind of ways to show that the unified generic expression that we came up with can kind of specialize or revert to well-known expressions that are used for different special cases. Now, the beauty of that once you have this expression, you can use it to, let's say, find the ergodic capacity, the Shannon capacity by averaging that expression of the capacity over this distribution. Things can be done closed form, and the final result can be expressed again as a G function, as function again of the parameter alpha, beta, and so on. You can also look at asymptotic kind of results. So because sometimes people argue that it's not always nice to deal with the G function. So if you do an asymptotic expansion of the G function, you can write the asymptotic result like here you see as function of very simple finite sums. This is for the high SNR regimes. We have even expressions that are more compact, but they're function of other special functions like the psi function, the gamma function. In the low SNR regime, the expressions are very simple also. So we have this kind of expression in our papers. If you wish, you can look here at the capacity as function SNR. You have the exact expression here for different C parameters, and you have the asymptotic results that are essentially plot just like here the bounds to show how good they are at high SNR regime. And here we see also high SNR regime for the IMDD case. Now, if you want to move to low SNR regime, then we can see that how the simulation are matching quite well. The asymptotic results are quite simple. So this is an asymptotic result in the case of actually log normal failing. We did also results for log normal kind of turbulence in the high SNR and low SNR regime, and we illustrate that how good are our results in this curve. And this is high SNR and this is low SNR kind of regime. Now, before concluding, I would like to mention that at the end of the day, FSO is not here to live on its own. It is here to be integrated with the rest of the ecosystem, which is in particular the case in the context of backhauling. For instance, you may end up finding yourself in a scenario where you have to connect two end devices through free space optic links, but one of these devices is going to act as a multiplexer or an integrator of multiple RF kind of links, and so you have multiple RF users being multiplexed, and each user can be, let's say, whatever, like 1 megabit per second. You multiplex 100 of these users, you end up with a backhaul of 100 megabit that has to go through an FSO link. What I'm trying to say here, often you find yourself dealing with dual hop systems where the first hop is going to be RF and the second hop is going to be FSO. So this is kind of an interesting set of studies that have been done by many groups worldwide about the analysis of dual hop mixed RF FSO system or mixed FSO RF system, where basically you have a backhaul being split among multiple users. So That's kind of the other way around. You have an FSO as a first hop, and then signal being dispatched to multiple users. So these kind of studies of FSO, RF, FSO have been studied. We were able to develop some interesting exact analytical results. I mean, again, they are in terms of the G function or asymptotically in terms of these finite sums. We tend to like these closed forms, and actually there is this interesting paper in 2013 that talks about closed forms and why actually they are useful, why having closed form allows you often to do some asymptotic results and get some insight or get some simpler expression out of these sometimes complex expressions. So bottom line, we were able to analyze multiple of these scenarios in closed forms, and they were published in the paper that I cited here by Emna Sedini for the RFSO and FSO-RF cases. And as a way to validate that, we show here the R probability of these mixed RFSO systems for both IMDD and heterodyne systems for different levels of turbulence, starting from weak turbulence in blue all the way to strong turbulence in magenta. And as you see, simulation results marked by these symbols match perfectly analytical results in solid lines. So we looked also at not only out probability but beta rate. Again, exact results in terms of the G function, asymptotic result in terms of these special functions, and we have a perfect match between these exact results that are obtained by simulation and these asymptotic result, and the match is exact at high SNR because they are asymptotic results. Finally, we looked at out probability of FSO RF system. They tend to be harder to analyze than RF FSO systems. Expression are in terms of these bivariate H functions. This is an even more complex function. We have in the appendix of this paper we wrote a couple of years ago a MATLAB way to kind of implement these bivariate H functions. But bottom line, we can express this out probability in terms of these bivariate H functions, and we were able to plot these kind of curves, this kind of expression, and again determine exact results that were validated by simulation. And we have also asymptotic results that were actually plotted to kind of validate what happens at high SNR. So with that, I would like to wrap up the first part of this tutorial. And my concluding remarks as far as this part is concerned is that spectrum scarcity is becoming a reality. It has been always a big important factor of our kind of designs. And because of this spectrum scarcity, one interesting solution is to go towards these extreme bands, this upper part of the spectrum, including the optical part of the spectrum. And when we talk about extreme optical part of the spectrum, we talk about free space optics. So there is quite a bit of interesting work that started on that for many years now, on the channel modeling aspect, on the performance analysis aspect. And of course, there is a lot of work that is being done and that needs to be still done on the test bed and on deployment. What I presented so far is really some kind of basic, I would say, channel models and system models. I would like now to give the hand to my colleague, Dr. Abdurrahman Trishili, who will talk about more advanced, let's say, mode of transmission, so based on structural light, in particular OAM, to explain how this field of FSO is moving over the coming few years. With that, thank you, and I will let you listen to my colleague, Dr. Abdurrahman Trishili. Thank you very much.
Thank you so much, Professor Slim. Good morning, ladies and gentlemen. My name is Abdurrahman Trishili, and as Professor Slim said, I will be talking on a relatively new trend in free space optics known as structured light. Before defining structured light, I would like to give you an overview of the techniques that have been used for optical networks in general to better use the channels and push the communication capacity. In optical communication, different signals can be sent over different time slots through the well-known time division multiplexing scheme. Independent data signals can be encoded on two orthogonal polarization states, which can double the capacity of a transmission system. It is also possible to encode different data streams on different wavelengths, which scales the capacity by the number of the used carrier frequencies. Data can be further encoded using advanced and complex modulation formats. All these techniques, based on the different degrees of freedom of light, have significantly contributed to satisfy the continuous need for higher transmission capacities. However, they are exhausted and may not be enough to face the upcoming zettabyte era as initially described in this tutorial. However, light has also pattern. We refer to these light patterns as special modes or structured light, with the pattern degree of freedom, or better known as the space degree of freedom. Since it's actually based on the light beam structure, it's possible to pack different data streams on different special modes, which can considerably increase the transmission capacity of an optical channel. This concept is known as the special mode multiplexing and was firstly suggested in optical fiber communication and then extended to free space channel. And the principle or the concept of special mode multiplexing, it's an addition to wavelength division multiplexing, polarization division multiplexing, and time division multiplexing. So for one particular light pattern, you can use multiple wavelength and two orthogonal polarization state, and you can send it over different time slots. Mode of choice for FSO special multiplexing is the orbital angular momentum mode. OIM is associated with the donut shape intensity distribution and the helical shaped wavefront, as you can see here, described by a phase term exponential IL phi, where phi is the azimuth and L is the topological charge of the OIM. L is an unbounded integer and can take any value, and the difference between a positive L and a negative L is the rotation direction. It's either clockwise or anti-clockwise. The particular case of L equals 0 corresponds to the Gaussian beam used in single mode FSO or fiber communication. OIMs are orthogonal with each other, which means that they can be used to carry independent data streams, and in an ideal medium they can be demultiplexed without any interference, and therefore they can significantly increase the transmission capacity of an optical system. Orbital angular momentum should not be confused with spin angular momentum associated with the circular polarization. Circular polarization is related to the oscillation of the electrical field, as you can see here from this illustration. Spin angular momentum can have two possible orthogonal states, right-handed and left-handed, while OIM is associated with the special distribution of the field and give access to infinite number of states. For those who are familiar with optics, if we put a quarter wave plate in front of the spin angular momentum, it will disappear. The circular polarization will become linear polarization. However, if we put a quarter wave plate in front of the OIM, the beam will keep rotating. So keep in mind that here the polarization is rotating around the propagation axis, and here the phase is rotating, and the twist or the rotation of the phase is not the same from one beam to another. With the OIM multiplexing, we can have access to multidimensional multiplexing. For each OIM, we can use two orthogonal states and different wavelengths and different frequencies, and therefore considerably increase the transmission capacity. OIM is not only a beam of choice for communication, but also beam of choice for other immersion applications, such as optical manipulation and tweezing to move and manipulate tiny particles. Also, it's a beam of choice for quantum optics and high dimensional entanglements for quantum key distribution applications. It's also beam of choice for optical metrology and remote sensing to measure surface profiles, for example, and a beam of choice for optical imaging and ghost imaging applications. Thanks to OIM, terabit per second laboratory transmissions have been reported in the literature. with very high spectral efficiency levels over FSO links and also over optical fibers. And such transmission capacities have not been demonstrated before using any communication technology, neither fiber or radio frequency. OAM has also several other potential uses in communication. One of them is establishing high-speed indoor wireless connections, in particular in data centers. The idea is to install an optical transceiver on top of each rack of servers to communicate with the neighboring racks, and communicating between shadowed racks can be ensured via ceiling mirrors and wall mirrors. It is also possible, as you can see here, to use multiple wavelengths over the same link. This will potentially contribute in reducing the cabling complexity and reduce the energy consumption in data centers while providing super high connectivity. OAM can be potentially used at the chip level as well to improve the performance of on-chip circuits. Each chip can have a set of optical transmitters and receivers to establish an optical connectivity with a neighboring chip. And this is actually suitable for a future generation all-photonics integrated circuits for future data servers and fast computing. OAM beams have also been suggested to increase the capacity of UAV FSO communications. Multiple beams can be multiplexed over the same UAV ground station link. A recent demonstration by Alan Winner's group from the University of Southern California has shown a 100-meter round-trip connection using two OAM modes, each carrying a 40 gigabit per second data signal. Another potential of OAM structured light is ensuring fiber FSO convergence. But before showing you how, I would like to bring your attention to the commonly used mode set for special multiplexing in optical fibers. These modes are known as linearly polarized and can propagate over long distances and have been well studied in the literature. LP modes are approximate solutions to the wave equation, meaning they are not exact modes and are not orthogonal with each other, which means that they can exchange energy while propagating over optical fibers, and this requires complex digital signal processing at the receiver. So, for example, this graph shows a DSP block used to separate six different LP modes after propagating over 33 kilometers. And this was one of the first special mode multiplexing demonstration using linearly polarized modes. However, in case of using OAMs over fibers, no DSP operations are required at the receiver to distinguish or to perfectly demultiplex the beams after propagation. In this case, OAM beams propagating in free space can be coupled to a fiber and then propagating over like several kilometers, and can be then demultiplexed and sent directly or like forwarded directly to free space link without any need for intermediate optical to electrical or electrical to optical conversion devices. Therefore, convergence between fiber and FSO links can be fulfilled via OAM beams. An additional exciting way of using OAM states is multicasting communication. Data on a particular OAM state can be duplicated and sent to different users over many OAM channels without decoding and re-encoding processes independently. This is independent from the propagation media or the application, either fiber or free space. The shape of OAM can also act as an information symbol. As I previously mentioned, OAM give access to infinite number of states which means we have infinite communication alphabet. This technique could be potentially used to establish a secure FSO communication scheme. So we have multiple patterns that are sent through media, then detected using a mode detector, then the communication can be decoded. One last potential of using OAM in communication is modal diversity. In single channel FSO, we have different diversity schemes to mitigate the effect of turbulence. For example, we can have time diversity by sending the same signal at different time slots. We can also have time wavelength diversity by sending the same information at over different wavelength. We can also have polarization diversity by duplicating the information over two orthogonal polarization states. And finally, space diversity by sending the same signal over different paths and use multiple transmitters for the generation and multiple receiving apertures. So with the structured light or with OAM, we can provide a new diversity scheme, which is denoted as or like commonly called as modal diversity. Modal diversity consists of encoding the same information over different modes co-propagating along the same path. So Mitchell has been very active on this topic and will later provide further information on his research on this topic. OAM can be generated using different techniques, including spiral faceplates, computer-generated holograms programmed on special light modulators, Q plates, and also meta surfaces. Other generation methods involve integrated compact devices based on silicon resonators, based also on metamaterials, and very recently vertical cavity surface emitting laser with customized OAM output was demonstrated. Last month, an emitter with the tunable OAM charges was also demonstrated. However, all these techniques are still limited in laboratory test benches and only limited for low OAM topological charges. There are also many detection techniques for OAM light, such as the use of computer-generated hologram also loaded on special light modulators, homemade mode sorters, meta surfaces, and homemade sectorial screens. So as takeaway messages for the potentials of OAM, OAM is an extra degree of freedom for optical networks, in particular for indoor and outdoor applications. Convergence between FSO channels and optical fibers can be ensured by the use of OAM beams without the need for intermediate optical to electrical or electrical to optical converters. OAM multiplexing offers a new diversity scheme, which is the modal diversity. And also there are several passive and active techniques that can be used to generate and detect OAM beams in the literature. After seeing the bright picture of OAM, now we should see the main challenges for the deployment of OAM in real life applications, and we will start with the limitation of the generation techniques. Among the OAM generation techniques that I showed you in the previous slides, these are the commercially available option. You can purchase a spiral faceplate, but it will allow you to generate a single OAM at a particular wavelength. You can also use a Q plate, but your incoming beam should have circular polarization. Usually each Q plate is only for a single wavelength and also for a single beam. But there are some Q plates that are tunable in wavelength. They have like a small bandwidth, Another option is to use a special light modulator, which will allow you to generate multiple beams depending on the hologram that is programmed on the SLM screen. But one thing in common for all these three methods is that they are bulky and requires strict alignment for experiment. In most of the major papers on the topic of OAM multiplexing, including ours, we use special light modulators. Special light modulator is an electronically programmable device with an LCD screen or an array of digital micromirror devices, DMDs. The one depicted here is based on the liquid crystal technology. And when shined with a laser beam, most of the incident light energy goes to an unwanted zero diffracted beam, the non-diffracted beam. We usually end up with a small portion in the first diffraction order. There are some ways how to increase the energy portion that goes to the first diffraction order, but it's not a straightforward task. And even with this, with all the ways that are to increase the energy that goes to the first order of diffraction, the process remains very lossy and not suitable for out-of-lab experiment. So in summary, here we compare the different OAM generation techniques in terms of conversion efficiency, wavelength tunability, complexity, flexibility, and costs. All these techniques has some issues, some has better performance than other, but also cost, but have higher cost than the other. And also some are complex, some are not, and some are flexible and some not flexible. But in practical, most of these techniques are not practical for out-of-lab experiments. Another challenge for OAM communication or structured light FSO is beam divergence. As it propagates in free space, any laser beam tends to diverge. For a Gaussian beam, the beam radius at any position Z along the propagation axis is expressed as a function of the beam radius at the transmitter, omega 0, and the Rayleigh range as follows. So the Rayleigh range of a laser beam is the distance in the propagation direction where the beam radius is increased by a factor of square root of 2. It means that the beam area is doubled at this range. In order to fully collect the beam at the receiver plane, the receiving aperture diameter should be at least 2 times the beam radius at the receiver plane. For an OAM beam, the divergence scales with L, therefore larger receiving aperture are needed to fully recover the initially encoded modes. And differently from Gaussian beams, we need to fully recover the OAM beam in order to decode the data. For example, if you have a Gaussian beam and you only capture half of the beam, that's fine. But for an OAM beam, you need to fully recover your beam of light. Which makes OAM beams very sensitive to pointing error as well. The problem of the divergence of OAM raised a lot of questions in many papers on whether the use of OAM is optimal or not. Structured light FSO or FSO based OAM is also subject to random propagation effects due to atmospheric effect. So while propagating through turbulent atmosphere, OAM beams tend to exchange energy between each other, and this phenomena is known as the intermodal crosstalk. The amount of loss per mode depends on the OAM order, and each OAM has its own mode-dependent loss. For an experiment involved in different OAM charges, we will have different received powers and therefore SNR imbalance. Professor Slim at the beginning of this tutorial has shown that many statistical models are available in the literature to model the effects of atmospheric turbulence in single-channel FSO systems. He presented exact forms for the outage probability, error rate probability, and channel capacity. He also presented exact forms that account for pointing errors. However, such a theoretical background is still missing for OIM and structured light communication. Emulating turbulence in OIM FSO systems can be performed through the use of random phase screens generated from the power spectral density of the fluctuation of the refractive index of the atmosphere. Two main models are used to model the refractive index fluctuations. The first one and the oldest one is the Kolmogorov model, which is considered to underestimate the effect of turbulence, and the more generalized one is the modified Van Karman model, which accounts for small scale variations in the order of a few centimeters and large scale variations in the order of a few hundreds of meters along the propagation path. Emulating the effect of turbulence can be done by placing multiple independent random phase screens along the propagation axis. The phase screens are basically the 2D Fourier transform of this quantity, which is the power spectral density of the fluctuation of the refractive index of the atmosphere. So one numerical model to simulate the propagation through multiple phase screens is the well-known split-step Fourier that is based on the Fourier and the inverse Fourier transformations. Here how structured light beams look like when propagated through different turbulence regimes. The first case corresponds to a weak turbulence regime. The second case is for a moderate turbulence regime, and the third case is for a very strong turbulence regime. These beams were simulated using the previously mentioned split-step Fourier method, and the propagation distance for the simulations was 1 kilometer. Of course, FSO links may also be physically tested in a laboratory environment. The first method is through the use of thin glass plates. The second method is through computer-generated holograms loaded on special light modulators. It's also possible to emulate the effect of turbulence in lab through the use of homemade chambers. So those are two chambers that we used before in some of our FSO laboratory demonstrations. The first one is used to simulate the effect of dusty weather, which we sometimes experience in our region. The second one is perfect to emulate the effect of weather of humid weather and to emulate the effect of fog. Here are some takeaway messages from this part of the presentation concerning the OIM deployment challenges. Beam divergence, which scales with the beam topological charge and requires large receiving apertures, larger than those for Gaussian beams. The beam needs to be fully collected in order to decode the initially encoded data, which makes OIM beams very sensitive to pointing error. OIM propagation through turbulence result in more dependent loss and therefore SLM imbalance, and also intermodal crosstalk, which consists of the exchange of energy between the co-propagating modes caused by the randomly varying turbulence effects. Some other major challenges for OIM communication include the lack of theoretical framework for turbulence modeling and the lack of proper generation tools. After we have seen the challenges for OIM-based FSO communication, in particular those created by atmospheric turbulence, now we move to the perspectives of OIM, in particular the turbulence mitigation strategies. Several techniques have been proposed in the literature to mitigate the random turbulence distortions in free space. Turbulence effect mitigation can be performed at the beam level through adaptive optics or through mode selection or through crosstalk precoding techniques, or at the digital signal processing level through space-time coding, error correction coding, and equalization. Here we will mainly focus on corrections at the beam level, in particular those using adaptive optics. Adaptive optics is a technology used to improve the performance of optical systems by reducing the effect of wavefront distortions caused by atmospheric turbulence. This technology was brought to FSO from astronomy, and it aims to correct the deformations of an incoming wavefront through a wavefront corrector unit. The wavefront corrector unit can be a liquid crystal array, which is typically slow, or can be an array of deformable mirrors, which is fast enough to perform real-time correction. Here an example of an adaptive optics system. Before the correction, the amount of wavefront distortion on a beacon beam whose shape is known to the adaptive optics unit is measured by a wavefront sensor. The information about the distortion is forwarded to a control unit, which computes suitable inverse or correction phase, which is applied to the wavefront corrector to correct the incoming wavefront or the incoming information carrier beam. There are two possible schemes for adaptive optics. The first one is a post-correction scheme, where the distorted light beam is corrected at the receiver plane. In this case, the adaptive optics system at the receiver relies on a beacon beam that is sent by the transmitter to determine the impact of atmospheric turbulence before applying the right correction function. A second adaptive optics approach is a pre-compensation approach. In this case, the transmitter requires a beacon Gaussian beam or to estimate the impact of atmospheric turbulence on the information carrier beam. The transmitter will apply a distortion function to the beam. So when the information carrier beam propagates through atmospheric turbulence, the pre-distortion will be cancelled, and at the receiver plane we will end up with a nearly pure beam. Another way to compensate for atmospheric turbulence effects is through the use of cooperative diversity schemes. 7 or 8 years ago, this was a hot research topic. Two relay schemes are possible. The first one is amplify and forward, and consists of electrically or optically amplifying an optical signal, which is sent by a source node S and received or collected by a relay node R, and then amplified before being forwarded to a destination node D. So the amplification can be optically or electrically. An optical amplification for an amplify and forward relay is not accessible for all the wavelength for FSO, since there are no available optical amplifiers for some wavelengths. The second relaying scheme is decode and forward, which is quite complex compared to the amplify and forward, and consists of decoding the beam at the relay node before regenerating the beam and forwarded to and then forwards it to a destination node D. Both relaying schemes are quite useful for single mode FSO, but might be very challenging for OAM free space optics. However, for OAM or structured light links, we can rely on a third relaying scheme or approach that we define as correct and forward. The idea consists of applying correction on an incoming beam from a transmitting node using an adaptive optics kit, and forwarded to a receiving node. A single relay with an adaptive optics capability can be used in full duplex transmission. A less complex approach is through the use of a collimate and forward relaying approach. No correction is done at the relay node, only collimation through a telescope, which can significantly solve the divergence problem. So we can rely on two pre-compensation adaptive optics systems in each of the communicating sources. And this should be low complex compared to the collimate and forward approach. One of the negative arguments in the papers questioning OEMs is that the use of OEM could be outperformed by any complete model basis to scale the capacity of a communication system. However, OEM is only a subspace of the full Laguerre-Gaussian mode basis. So the LG beams form a complete orthonormal basis and are characterized by two main indices, the azimuthal index, which is the topological charge, and the radial index. So those beams have 2 degrees of freedoms. And OEM, when we say only OEM beam, it's an LG beam. It's an LG beam with a radial index of 0. The intensity distribution, the transverse intensity distribution of LG beams is depicted here, and higher radial index beams are able to propagate in a similar manner as OEM only beams, following the M² rules. A few years ago, we were among the first to demonstrate that it's actually possible to encode information over the full Laguerre-Gaussian mode basis using supercontinuum laser and two special light modulators. We were able to generate and detect a total number of 105 modes over 3 different wavelengths. So basically 35 modes per wavelength. Here is the crosstalk graph for all the 105 modes, which shows relatively high purity for all the generated modes with minimum intermodal crosstalk, which is mainly caused by some alignment and equipment imperfections. Another complete mode basis for FSO is the Hermite-Gaussian family. Each Hermite-Gaussian is characterized by 2 degrees of freedom, M and N. Mitchell, in one of his experiments, he showed that Hermite-Gaussian are more resilient to atmospheric turbulence compared to Laguerre-Gaussian modes, and also the mode-dependent loss for Hermite-Gaussian modes is 50% less than the mode-dependent loss by Laguerre-Gaussian modes. He will later provide some further information about his experimental results. Recently, with our collaborators from King Saud University in the capital city of Riyadh, we started working with the Hermite-Gaussian beams for index modulation communication application. We use a set of Laguerre-Gaussian beams and combination of Laguerre-Gaussian beams together with Hermite-Gaussian modes or Hermite-Gaussian beams as code words at the transmitter. Then we applied the deep learning algorithm at the receiver to detect the various light patterns after propagating through dusty storms. More details about this experiment are in our recently accepted publication. Another mode basis that could be of interest for spatial mode multiplexing is the Bessel mode family. In theory, a Bessel beam has an infinite number of rings and can carry infinite power, and it is able to reconstruct itself after encountering an obstruction. The electric field is expressed as follows and contains 2 main parameters, which are the azimuthal index L, responsible for the orbital angular momentum, and the radial index Kr, or radial spacing. These beams are approximated in practice via Bessel-Gaussian beams, and Bessel-Gaussian beams are non-diffractive over a finite region and can carry orbital angular momentum and can be used as information carriers as demonstrated in the literature. The electric field of a Gaussian beam is the same as the non-diffractive one, but modulated with a Gaussian function. Here we have an illustration of the self-reconstruction process of abyssal Gaussian beams after being blocked by an obstruction along the propagation path. As you can see here, we placed an obstruction along the propagation axis of abyssal Gaussian beam, and the beam started to reconstruct itself after propagating for a few centimeters. The main challenges for using those kind of beams, for this kind of beams, are the generation and detection techniques, and those beams only exist over a finite region of space. They disappear after propagating over a certain amount or a certain distance along the propagation axis. Recently, we have started to work on the design of small footprint generation techniques to make structured light FSO a reality outside of laboratory test benches. The idea was to design microscale spiral faceplates that are printed using a 3D nanoscribe printing machine that we have here at KAUST. The 3D printed spiral faceplates can be easily integrated with laser sources and have a high conversion efficiency, meaning if one of the plates is shined with a laser beam, more than 98% of the light will go through the plate. The printing process is also not complex, and the printed plates are easy to work with and are easy to align. Here are some tiny spiral face plates printed on a glass substrate. Each has a radius of 20 micrometer. Each SPP allow for the generation of a single beam. Here we have a topological charge of 1 plate. We have L equal to 2, L minus 3, and L plus 4. The obtained interferograms observed on CCD camera are of good quality. This type of interference patterns is formed when a Gaussian laser beam with a transverse size larger than the fabricated spiral faceplate passes through it, resulting in interference image formed by the generated OAM and the unperturbed Gaussian parts of the beam. By checking the purity of the obtained patterns using a special light modulator for the beam detection, we found that the generated OAM by each of the 3D printed spiral faceplates that we tested is of high purity. You can see here slight crosstalk, which is mainly because of small alignment imperfections, since we were moving the glass substrate here by hand. We were moving it manually, basically. To test the performance of the 3D printed spiral faceplates, we used them to establish a near-infrared FSO link on a laboratory test bench using a bit error rate tester, laser diode, and a special light modulator for the demultiplexing, and an avalanche photodetector to decode the data. At 1 gigabit per second data rate, the communication was error-free. When we increase the data rate, the BAR level also increases. But the main issue was the bandwidth of the used photodetector here. and this actually confirms that the printed plates are suitable for high throughput transmission. Previously, I had another slide after this one, but I decided to remove it since the work is not yet published, but I can give you an overview about the content. We recently built an integrated device, an integrated laser that can emit OIM modulated light and can be easily deployed for FSO links. So hopefully it will appear soon in one of our papers. So after we have seen the potentials, challenges, and perspective of OIM, here are some takeaway messages. In order to make structured light FSO a reality, we need to develop more realistic atmospheric turbulence models. Adaptive optics can be used to perform correction at the beam level. Applying relaying methods with correct and forward and collimate and forward capabilities can potentially reduce divergence and turbulence effects. Complete bases can serve as good alternatives to OIM, and out of laboratory deployments are not possible without or are very difficult without integrated OIM laser sources. Now I will leave you with Dr. Mitchell Cox, who will be presenting how FSO can potentially help to tackle the digital divide in rural areas and scattered communities. And thank you.
Hello, ladies and gentlemen. My name is Mitch Cox, and I'm from the School of Electrical and Information Engineering at Wits University, otherwise known as the University of the Witwatersrand, in Johannesburg, South Africa. I'm going to be talking about bridging the digital divide with a South African perspective. This talk follows from what my previous two colleagues have spoken about, where you received a bit of background into FSO and structured light. I will start with talking about what the digital divide is, and proceed to talking about how FSO may be a solution, and some interesting work on structured light as they pertain to bridging the digital divide. How many of these logos do you recognize? Probably most. This just goes to show how embedded apps are in our lives, and how we make use of the internet every day. That's not the only thing. The world is getting smarter. Some call this the fourth industrial revolution. Things like self-driving cars, automatic traffic management, 5G connectivity, and maybe even artificially intelligent CCTV systems are probably only the tip of the iceberg of what's to come, provided there's enough internet capacity. Did you know that only 24% of African people use the internet, compared to almost 80% in Europe? This doesn't bode well for a smart future in Africa anytime soon, among several other things I'll talk about later. Africa has about 17% of the world population. This means that about 1 billion people in Africa don't use the internet. If we zoom in a little, we can see that a few countries in Africa, namely South Africa, where I'm from, Nigeria, Morocco, Egypt, and Kenya, have significantly more users than other African countries. Many online services assume good internet connectivity, but this isn't always the case. Moving in further to South Africa, we see that there are areas where there is high population density, but quite a long distance to fiber. This is shown on those red patches on the map, resulting in slow internet connection speeds for the people who live there. You can also see that the average internet connectivity in most of Africa is somewhere probably less than about 6 megabits per second. This is pretty slow compared to first world standards. This presentation aims to provide some explanation as to why this is, and of course some possible solutions in an optics context. First, a history lesson. In around 2001, South Africa got its first undersea optical cable. I remember at the time it became possible to get capped ADSL, and when I think back, I wonder how I managed with 3 gigabytes at 384 kilobits per second. Several years later, the CCOM cable enabled uncapped ADSL lines for people, and a few years after that with the wax cable, fiber to the home became affordable and now is pretty common. Overall, Africa appears to be quite well connected in terms of undersea optical fiber. South Africa, for example, has a total of about 50 terabits per second capacity, and it's not all used yet. The new Equiano cable, which is the world's first space division multiplex undersea fiber, is 100 terabits per second just itself, but it's for Google's exclusive use and doesn't count towards general internet capacity, at least in a direct manner. To put this into perspective, a relatively recent cable between the USA and Portugal called the Maria cable is 160 terabits per second alone. The real issue in Africa is terrestrial connectivity. There's a mismatch between where people live and where there's fiber. You can see in Central Africa there are relatively few fibers compared to the darker red on the plot on the top right, which is population density. The orange lines on the left are existing fiber, and the red lines are fiber under construction. It's quite clear that where there is more fiber, there are more internet users, if you have a look at the bottom right. It seems like the problem is being solved, but the space between fibers is actually really vast, as you'll see soon. In Johannesburg, where I live, connectivity isn't really an issue anymore. My university, with the photo on the bottom left, is situated in Joburg, and you can see there is a high concentration of fiber in the area. Almost all the suburbs in and around the city have fiber to the home, which is quite affordable, with ubiquitous 4G connectivity and even some 5G. Unfortunately, cities like Johannesburg are the exception. Many people live in rural villages with poor internet connectivity. In South Africa, other infrastructure such as electricity and running water is generally available, but I can't say the same for all African or maybe just developing in general countries. Much of Africa is wild, with long distances between human settlements. This makes installing fiber more challenging in some ways, as there aren't necessarily tar roads to simply bury the fiber along. This is a real photo that was taken a few years ago just behind my university. Lions don't usually roam the streets, but sometimes a television advert requires it to drive the wild point home. The real issue with installing fiber in Africa is that Africa is enormous. As visible in this illustration, all of Europe, China, the USA, and India fit quite neatly into the area of Africa. Think about that for a little. Remember the picture of terrestrial fiber in Africa? Those gaps in Central Africa are almost as wide as entire European countries. A few years ago now, Martin Lavery, Andrew Forbes, and I hosted a small workshop at a game reserve near Johannesburg on tackling Africa's digital divide. We discussed some crazy and some good ideas on how we might use optical technologies for this purpose. But to start, I would like to go over some interesting statistics. South Africa, which is relatively well connected, as you remember, has a last few miles challenge. This image shows the population density as dots where there are at least a few hundred people of the country, with the color representing their distance to the nearest fiber, red being further away. 67% of the population of almost 60 million people are within a kilometer of fiber, and 99% are within 20 kilometers. To get all the so-called anchor sites in the country connected to existing infrastructure, in other words, to connect schools, clinics, and police stations in unconnected areas, it would take another 62,000 kilometers of fiber, and that is if the fiber is laid in a straight line. This isn't typical, and if the fiber were to be laid along roads, it would take about 85,000 kilometers. This is a lot of fiber, and South Africa is already relatively well connected. Given that fiber costs on the order of $100 per meter to install, the cost is huge. If South Africa had no existing infrastructure, just for fun, a greenfield installation would require a minimum of 159,000 kilometers of fiber. This is obviously unrealistic, and the routing alone would destroy your connection latency, but it's still interesting. This is probably true of most countries, but mobile networks are great for the access network. In 2015 in South Africa, 99% of our population had access to 2G, which to be blunt is pretty slow and useless for modern web apps today. But by 2018, 99.9% of the population had access to 3G. In 2018, about 86% had 4G or LTE coverage. Smartphone penetration is also quite good, with about 82% of phones being smart 2 years ago. This all seems great. Most people have smartphones and access to 4G, so what is the issue actually? I believe it comes down to two things. Technically, just because your phone has 4G, it doesn't mean the connection to the base station is fast enough to deliver 4G speed to everyone. Secondly, data costs money. Allow me to explain with a short story. A few years ago, Vodacom, one of our large mobile service providers, decided to try to get everyone off the old 2G network, as it's obviously simpler to maintain a 3G network and decommission the 2G one. They went to a village and gave everyone a 3G enabled smartphone and asked them to use them instead of their old Nokia 3210s or whatever they used. They monitored the network usage, and strangely, after about a month, everyone had gone back to their 2G phones. They went back to the community and asked them why. It turns out that because smartphones tend to do a lot in the background, coupled with the fact that it's easy to use data inadvertently, like a YouTube clip jumping to 1080p, they use a lot of data in a somewhat uncontrollable manner. This costs money, and in places where people go over to their neighbors to boil the kettle because they've already used up their free electricity allowance, this is not affordable. The cost of data is one of the leading causes of the digital divide. Internet access costs money, and Africa isn't the richest continent, money-wise at least. If we look at the gross domestic product, or GDP, of the USA, it's about $19 trillion. South Africa's neighboring country, Mozambique, is a meager $12 billion, and South Africa is a decent $350 billion. That's only a little more than Apple's annual turnover. In percent, most African countries have a GDP on the order of less than 1% that of the USA. It's not entirely fair to make this comparison in absolute terms, but if we normalize to population, the average American makes $60,000 per year. A South African earns a tenth of that at around $6,000, and in Mozambique, around $400. That's definitely not enough to pay for fiber to the home or a fancy 5G-enabled cell phone. The Human Development Index is another interesting metric to compare countries. It is a measure of people's average life expectancy, their level of education, and their standard of living, which is measured using how much money they have. You might be wondering if the internet can be used to raise a country's Human Development Index. I think so. There are numerous online medical resources, and expert systems such as IBM Watson could be used in future to diagnose common and maybe even rare illnesses in the absence of a local specialist. Robotic surgery is also an emerging technology. There are also numerous online education resources. Some are relatively informal, such as YouTube or blogs or maybe even Wikipedia, and some are more structured, such as edX or Coursera, to name a few. Of course, with global lockdowns and quarantines, there are also online conferences like this one. Importantly, a lot of these resources are free. Lastly, there are plenty of ways to make money using the internet, both formally and informally. I want to talk about this last one in a little more detail, since economic growth naturally brings benefits to the other two. The internet is an economic enabler. I think this probably goes without saying, but to highlight this fact, the ICT sector contributes about 6% of the UK's GDP. There are also many ways of earning money with an internet connection, some of which are irrespective of your geographic location. One could become a viral YouTube vlogger or a graphic designer using open source software on freelancer.com. With self-taught programming skills, someone sitting in a village could create apps for mobile app stores and sell them, or even become an Uber driver. Probably the most accessible ways of making money online is by dropshipping things from countries such as China to wealthy people living in cities around the world. Who's to say that awesome XYZ electronics store on eBay is actually someone living in the middle of nowhere? There are many technologies at our disposal to bridge the digital divide. Subsea fiber is ultimately the backbone of the internet, and it is easy to connect areas that are close to these using fiber. Point-to-point microwave links were historically used for backhaul before the days of fiber, and are still in use today in certain situations. Free space optical technology may provide a retrofit alternative to this, with faster and more reliable fiber installed at a later date. To access network could use radio or optical, and there are some interesting projects in this regard, such as weather balloons and such. By now, many of you have probably heard of Starlink, which could one day be an alternative to many of these technologies. Based on what I've read, it appears that the idea is to have a high-speed 20 gigabit per second mesh network between the satellites in space. Since radio is used to the ground, I guess that only megabits per second speeds would be available to users with reasonable latencies. The sky is the limit, however, and if FSO technology were used to the ground, the speeds could theoretically be much faster than with radio. Radio communication is slow and spectrum congested. Slow is of course relative, but a cutting-edge communications satellite can only sustain several hundred gigabits per second, which isn't really that much for the cost of launching one. Long-range Wi-Fi, as seen in the middle photo, can support a few hundred megabits per second over a few kilometers, and carrier-grade wireless, such as millimeter wave, supports gigabits per second also over a few kilometers. Fiber optic links, on the other hand, can support terabits per second with careful design, and hundreds of gigabits per second relatively easily. Assuming fiber is too expensive to install over these long distances, a possible alternative to radio is free space optical communication. On the left is a South African system that supports 1 gigabit per second over 1.5 kilometers with very high reliability, and on the right is a Russian system that can do 30 gigabits per second over the same distance. FSO has been described as fiber without the fiber. The capacity of an FSO link is straightforward to increase using technology from fiber such as wavelength and polarization division multiplexing. Unfortunately, however, the range is currently quite limited, as atmospheric turbulence is a significant challenge, as you will have seen earlier. This scatterplot shows commercial systems as red stars and a selection of seminal experimental systems as blue diamonds. The best commercial system in terms of speed and range is 5 gigabits per second over 5 kilometers, which is quite a lot better than the competition. It is important to remember that there is a specific link budget, and most systems will go further in clear weather. Weather isn't always clear though, and there isn't a standard way to report range. Some systems are more conservative and assume the worst case, where reliability is the primary concern. Other systems assume range is of primary importance, and so the reliability isn't necessarily 99.9% at long range. There are several commercial systems which can sustain 1 to 30 gigabit per second over ranges up to 5 kilometers, but it appears that 5 kilometers is currently the frontier. I've highlighted the region over 5 kilometers and 5 gigabits per second, where you can see there are no commercial systems at the moment. I believe this region is where we need to focus research and development in order to have FSO solutions that can be used to bridge the digital divide. I'm now going to briefly go over some research highlights in areas of optics and photonics that are helping to push this frontier, both in terms of bit rate and range. As discussed earlier by Abdurrahman, structured light is a relatively new area of research which holds promise for FSO. The top paper is the first demonstration of so-called orbital angular momentum modes or mode division multiplexing. On the left is the fastest transmission to date of about 1 petabit per second over a lab bench, and the furthest MDM communication link in free space is only currently around 260 meters. On the right is an experimental setup of a typical lab experiment for mode division multiplexing, this one being 500 gigabits per second in strong simulated turbulence. We've been working on several different approaches to improving the range of free space optic links, mostly looking at structured light. Here you can see me on the left, with Andrew Forbes' group who's on the right, a few years ago, where I did my PhD. We're working together on several different approaches to increase the range of FSO links. Vector vortex modes are OAM modes with a spatially varying polarization, as you can see on the top right of the slide. Scalar vortex modes are the classic OAM mode, with a uniform polarization as seen on the top left. At the time, there were several papers claiming that vector modes were more robust in atmospheric turbulence than their scalar counterparts, but not much explanation why. I asked the question whether this was the case and did the experiment. You can see the experimental setup here at the bottom, which uses so-called Q plates to generate the modes, and a polarization invariant spatial light modulator setup to simulate the turbulence. This is because spatial light modulators can only modulate light with a horizontal polarization. We found that in all turbulence conditions that we tested, given by the so-called Strel ratio, the performance is in fact identical within the error of the experiment. Here we show crosstalk percentage, which is how much of the mode spills over into another mode on average. Crosstalk is obviously not a good thing in a mode division multiplex system. As a result, one should use whichever mode set is most suitable for the application based on the properties of the modes, but not because of their resilience to atmospheric turbulence. Are there structured beams that are indeed more resilient to turbulence though? Let's look at what turbulence actually is. In 1976, Knoll showed that turbulence can be broken down into a weighted sum of different component aberrations in the Zernike basis. The phases of the aberrations are shown here. On the left is tip and tilt, well actually tilt and tip, then defocus, astigmatism, and so on. It is interesting to note that about 90% on average of the effective turbulence is tip and tilt. This is easily compensated for by a simple adaptive optic mirror, not even a deformable mirror. But are there modes that are resilient to this without adaptive optics? If we consider the modes on the left column being OAM and Hermite-Gauss, for the correct detection of these modes, precise alignment is required. The arrows in the center indicate the axis that the mode is resilient on. For example, you can see OAM modes can be rotated without affecting their detection, but any translation due to tip and tilt will cause crosstalk into neighboring OAM modes. The Hermite-Gauss modes, or HG modes, are not resilient to rotation, but they are resilient to tip or tilt, depending on the orientation of the mode. For example, the HG10 mode on the bottom left will still be detected correctly even if it moves left and right. For the higher order modes, we assume the same. However, the HG11 mode, which is symmetrical, and perhaps other symmetrical HG modes too, will not be resilient as far as our hypothesis is concerned. And the results agree with this. Let's consider the bottom row, which is percentage crosstalk from one mode to the other. As before, turbulence causes crosstalk, but if a certain mode experiences less crosstalk in the same turbulence, then it is probably a better choice in an FSO system. If we look at the plot on the bottom left, we see that the HG modes, which are green, from the previous page with the HG11 mode excluded, are significantly more resilient in stronger turbulence than LG modes. When the HG11 mode is included, on the bottom right, the performance of HG and LG bases are essentially identical, which agrees with common understanding. The choice of mode clearly affects the performance of a system. So could we use this difference between modes to our advantage? In this variant of modal diversity, we use identical order modes, in other words modes with the same size and same divergence characteristics, from different bases. Each mode is propagated with the same data but half the intensity when one mode is used. This is to keep the overall intensity the same for comparison. Here I show an LG L equals 2, P equals 1 mode, combined with the Hermite-Gauss 2-2 mode, as they are orthogonal to each other and both have order 4. Modal diversity, as shown by Abdurrahman earlier, uses different size OAM modes, which would certainly experience different turbulence. In this case, however, a diversity gain is not expected according to conventional theory, which doesn't predict a modal dependence to turbulence. The results show that there is indeed a significant diversity gain. The bit error rate is quite bad in general here, but the solid lines representing diversity are clearly below the dotted lines which represent the individual modes. As an aside, we still see HG performing better than LG. In the same turbulence, the larger modes are affected less, as expected, shown by the purple line compared to the yellow line. I have plans to redo this experiment in real atmospheric turbulence in my lab, and I look forward to seeing the result, because a diversity gain without multiple apertures would indeed be quite useful for compact systems. You may have noticed that most of the interesting effects of turbulence I've presented so far relate to tip and tilt. I have one more thing to tell you about that. In this work, we built a 150 meter free space link and measured the movement of the beam at 300 frames per second. On the left is a comet plot of the centroid position over time. Notice that the beam does not really bounce around randomly. On the top left, the centroid positions are shown, connected with blue lines. There is a clear average Gaussian shape as expected. The red lines, here, are arbitrarily placed for illustration, but let's assume that they show the extent of the detector. If the beam wanders over this line, bits will be lost. If the beam stays outside the circle for an extended period of time, a potentially catastrophic loss of data may ensue. The bottom left shows the same position data, but limited to a single axis. If we plot the centroid positions against their previous positions, as shown on the bottom right of this slide, There is a clear correlation. This is important because in a communication system, this leads to what is known as a bursty channel. A common example of a bursty channel is in power line communications. Techniques do exist to deal with this sort of channel, but conventional models do not account for this. As such, protocols, error correction, and DSP designed for fiber or radio, where this effect isn't as significant, are suboptimal. Unfortunately, there are no models for this phenomenon in turbulence. All existing models of beam wonder are based on memoryless probability distributions. Another way of looking at this phenomenon is using a run length distribution. This is simply a histogram of the consecutive number of samples the beam spends inside or outside the circle on the previous slide. In other words, this is a histogram of the length of the fades. The green bars show what is predicted using models that use a memoryless probability distribution. The more samples generated, the longer the slope, but the overall slope shape will not change. In a system with memory or correlation, there may be artifacts in this distribution. For example, the tail shown here. On the left is the run length distribution of the measured data. There is a clear mismatch to the existing model, which led me to investigate a new modeling approach. I don't have time to go into all the details, but if you're interested, please take a look at the paper on arXiv. Suffice to say, a correlated time series model, such as an autoregressive moving average, happens to be an excellent fit for this if we think of the movement as a correlated random walk, not just a true random walk. Knowledge of the beam's movement with time enables us to do more than just optimize error correction algorithms. Since modal crosstalk is related to the movement of a beam, as made quite clear by the previous research I've shown, the ability to accurately predict its evolution may prove quite valuable. So where to now with structured light free space optics? There isn't a difference between scalar and vector modes. HG modes are more resilient to turbulence than LG or OAM modes, but they would allow for longer range links. Evidence so far indicates that modal diversity does work, which opens up some new areas of research in investigating in existing turbulence theory, but importantly allows for a more compact system with only one aperture. And lastly, beam wonder has memory, the knowledge of which will hopefully enable the development of better error correction and signal processing schemes for free space optics. So currently the digital divide is vast for geographic and socio-economic reasons. But by using new technologies and future development of existing systems, I hope that we can turn the digital divide into a digital opportunity. Thank you very much.
Good morning. My name is Bun Ui. In the next 30 minutes or so, I'm going to discuss the high-speed optoelectronics for visible light communications, or the VLC. We know that optical wireless communications can be broadly classified into 4 different categories. Free space optical communications, or the FSO. My colleague has been discussing quite a bit about this, using mainly the near-infrared light, 750 nanometers, all the way to about 1600 nanometers or so. This class of components are quite well developed for fiber optic communication. And the second one is visible light communication, VLC. And sometimes we also refer it as Li-Fi, because this technology ideally has the potential to complement the current Wi-Fi technology to provide more bandwidth. And conventionally, people has been using LED technology in the visible range, starting from violet color or go all the way to far red or so in 700 nanometers. Components developed for VLC are common for underwater wireless communication. Water has very low loss absorptions, low loss at visible spectrum, and similar component, especially transmitter and receiver, can then be used for underwater comm. And another one is the non-light of sight communications, or the so-called solar blind ultraviolet communications. It is in the ultraviolet range from 200 nanometers, which is UVC, band go all the way to UVA in 380 nanometers or so. In this talk, we are very much wanted to focus on the component or optoelectronic component that is being developed for visible light communications, laying on in the range of violet color go into the near or the far red region, which can find applications for VLC and also for underwater wireless communications. If you look at this particular spectrum, as I mentioned, unlike the near infrared component, which are very well developed over the past 40 or 40 something years, and for transmitter or the light sources available for the visible light communication, for example, it is only started in about 20-25 years ago. And thanks to the inventions of the LED, the blue LED by Suji Nakamura, who he eventually get a Nobel Prize in 2014 on these particular inventions, we then be able to use this as the light source for blue and green color semiconductor light source built on gallium nitride or the so-called 3-nitride material. And laser has also been demonstrated. And in COWS, instead of working on the LED and laser diode, we focus on another class of light emitting diode called superluminescent diode. I'm going to talk a little bit about this thing later on. And other component for manipulating light for VLC, for example, modulator, photodetector, and also the optical amplifier, and all that are not that matured technology for making those are still at the very early stage in the past few years, the most up to about 10 years or so, but still a lot of things need to be done. At COWS, we are the first group to use semiconductor laser to generate white color light for solid state lighting. So in this talk also, I'm going to talk a little bit about those, why semiconductor laser. And we also introduce the system that we developed for visible light communications in underwater, and also would like to talk a little bit about those things, about those topics. Let's go into the high-speed transmitter. LED, as I mentioned, is conventionally being used. If you excite a yellow color phosphor with the blue color LED, essentially you'll be able to get the white color LED. So white color LED can then be used for lighting system. That is the light bulb that we has been using quite a bit now. And if you look into the modulation frequency for such devices, the bandwidth of a typical LED is always limited to about a few tenths of megahertz. And that is very much limited by the carrier lifetime, because carrier lifetime of the LED in the spontaneous emission regime is always in the order of nanosecond. And also the chip size is really big. That will introduce a lot of the RC, parasitic capacitance and resistance that slow down the speed. And phosphor is also very, very slow devices. Phosphor, the bandwidth of phosphor usually is about 10 megahertz or so. So that will limit the modulation speed of the LED as a transmitter. If you want to transmit very high speed signal, will be quite challenging. Dominic O'Brien from Oxford, he did a very good comparison as of the bandwidth of various different LED sources. Some of them are still under research, but as you can see, for most of the commercial available product, we only get about a few tenths of megahertz of bandwidth. The only one that go beyond gigahertz is the nanowire based LED, which is still under research. The power is still an issue, and the reliability of the product, the device is still very much an issue. But no doubt you'll be able to get up to gigahertz of bandwidth by using these novel devices. Early work on the LED as a light source for Li-Fi particularly, which is the visible light communications, was proposed by Harold Haast from Edinburgh University back in 2007, 2009 or so. He began to publish in this space by using commercial available LED to send certain signal. And of course, we know that in early day, modulation is using very simple on-off keying. And in these two papers, he did not mentions about the bit rate, but I guess in those early days, the speed of the LED will not be too high. And later on, Chen from CAS, Chinese Academy of Sciences, begin to push the bit rates to slightly higher, a few hundred megabit per second, by using a bit more complex or higher order modulation scheme. In this case, is QAM 16 QAM OFDM. The advantage and disadvantage of using LED. LED is, of course, very reliable. Enough bandwidth, maybe up to a few tens of megahertz or so, and is relatively long lifetime because you could be able to operate the entire device to almost forever. And disadvantage for LED is that it suffers from the efficiency droop. I'll talk about what is efficiency droop later on. And again, if you want to push the entire device to up to a few gigahertz or so, it'd be highly challenging. To achieve gigabit per second transmissions, people has been looking into using micro LED. So micro LED shrink down the size of the LED to a few tenths of micron, or in the order of 10 of micron or so. And since the size is small, we'll be able to modulate at a high speed. And by using PAM, for example, PAM4 and OFDM, people has been able to achieve 5 gigabit per second. And the early work has been demonstrated by Martin Dawson in Strathclyde and Glasgow's group, as well as Dominic O'Brien in Oxford. And one of the challenging for using micro LED is the power, because you can never get enough power from a small little element of LED. Let's really look into what is the limiting factor for LED modulation and the bandwidth. If you look at the LED, under the rate equations, the speed, how fast can you turn it on and off, is very much limited by the carrier lifetime of the device itself. Carrier lifetime means that for carrier to go up to the conduction band, recombine to give you light, that takes a little while, and it's in nanosecond. So the bandwidth then is limited to very much megahertz, a few tens of megahertz or so. Laser diodes is limited by the photon lifetime. Photon lifetime for laser is very short, it's in picosecond. So ideally, you should be able to, not ideally, it's in practically, you'll be able to get beyond gigahertz of bandwidth. Santa Barbara, UC Santa Barbara has been doing a very good comparison by using the LED and phosphor, be able to get a few tens as expected. And by using laser diode, they'll be able to push it to beyond gigahertz of bandwidth. When they're doing this in 2015, the limiting factor is not how fast can you modulate the laser diode, but it's the photodetector, because even until today, there is no visible photodetector that will be able to give you multiple gigahertz of bandwidth to make such a measurement. So in short, if you want to get into higher bit rate, laser is definitely a lot more attractive than the LED. Let's switch gear a little bit, talk about the evolutions of various different light sources. What we know about fire in early day until the fluorescent light. And currently, thanks to the inventions of blue LED, we now begin to use the LED lamp to save a lot of energy. In chaos, we begin to ask ourselves, what is the future? What is next step after the LED lamp? We believe that laser lighting will be the future, and in being able to incorporate or integrate the visible light communications capability into the light bulb, you'll be able to get a light bulb to play two functions. One is the lighting, the other one is communications. Comparing the LED lighting and the laser lighting, if you want to get a 60 watt equivalent from the LED, we need a footprint of about 11 square millimeter, because you need to have multiple LED integrated onto a sub mount before you be able to get to such a high lumen. And since LED is a spontaneous emission, which is the random radiations to all different directions and angle, And collecting all those light is highly challenging. As for laser, laser is focused beam. By using only one single laser with a footprint of with a size of about 0.3 square millimeter, you'll be able to get to 60 watt incandescent equivalent. Just now we mentioned a little bit about the efficiency drop. If you look at this LED, the red color curve, you'll be able to see in the low injections current, the efficiency can reach up to about 70% of the external quantum efficiency. When you inject more current into it, we are supposed to be able to get a constant efficiency after the diode is turned on. But due to some physical limitations, LED will not be able to do so. You will see a drop in the efficiency. It means that the device is not highly efficient to convert a lot of those injections or the energy into heat. As for semiconductor laser, we do not see that trend. We still see a constant EQE at high injections. That's another reason why laser under the high injections, you'll be able to get more light out of it, and it will be operated at a lot more efficient manner as compared to LED. We use a semiconductor blue color laser, 450 nanometers laser, to excite onto the yellow phosphor, the YAG phosphor, to generate white color light. That essentially is for the white light, the lighting application. And this is done in very early day, 5-6 years ago. And the color rendering index in this device, this class of device, is not that great. And we're very much talking about 58. 58 is compared to sunlight. Sunlight is CRI. The color rendering index of sunlight is 100. So which is still a lot of missing spectrum when we use this method to generate white color light. And when we integrate into the communication system by using a simple on-off keying, however, we'll be able to get up to, well, a few, 1-2 gigabit per second of data rate transmitted. This will be the early day in the so-called laser-based solid-state lighting and integrating with the Wi-Fi capability or the visible light communications capability. So since we know that the CRI is an issue because it's too low and it's not going to be comfortable for eye, we use a red, green, and blue phosphor and excite the red RGB phosphor by using violet color light. In this case, it's 405 nanometers violet light to get a better CRI. We managed to improve it to about 80. And we also managed to tune the color down to a bit more comfortable level, which is not too bluish. Bluish is the cool light. And warmer lights have a bit more yellow color light into it. So for warm light, it started at about 3000 Kelvin and below. And anything at the 4000 Kelvin or so is being called as a cool light, which has too much blue color. And doing so, we also integrate into the, try to modulate it by using a simple OOK method to get about 1.25 gigabit per second. Phosphor is an issue because phosphor always is a very slow component or element and always slow down the entire modulation system. So in 2016, we integrate a new type of phosphor called perovskite quantum dot-based phosphor integrated into the red color light in order to increase the CRI to a very significant level, which is close to 90. Close to 90 means that we only have few sun spectrums missing to match the sun spectrum of CRI of 100. And the color temperature now is becoming warmer because we tune it in that way to get into about 3000 Kelvin region. Yet we still being able to keep to above 1 gigabit per second of modulations. And this will then close to the so-called good quality white color light for dual applications for both lighting by using laser and also by sending very, very fast signal through the VLC system. In the lab, we also look into how to increase the functionality of a small little chip. That is the laser diode. For example, we did quite a bit of work on integrating a modulator, the electro-absorption modulator, along the laser cavity. And we see that in our case, we managed to have a on-off stage by only applying a very low voltage of about 3.5 volts. Research is still ongoing because integrating any element into the laser cavity is highly challenging. And we also integrate a photo detector at the back of our laser diode to monitor the power. And we also have successfully integrated a semiconductor optical amplifier to the laser diode. In that case, we would not need to over-inject current into the laser sections or the so-called gain sections to overheat it that go into the thermal rollover to get a low slope efficiency. And amplifications of photons for the laser light in this device can then be done by using the semiconductor optical amplifier. For other new type of high-speed transmitter, we are very much looking into super luminescent diodes. We talk a little bit about the LED, and we talk about the pro and cons of using the LED. And efficiency droop is always the issue. Bandwidth is always the issue. And laser diodes, although it's droop free, even high injections, you still be able to get into very constant external quantum efficiency, and bandwidth is always gigabit per second. But whenever we talk about generating white color light using laser diode, people are always concerned about the laser light, how safe it is. And although in Europe, some of those high-end Audi car and also BMW already have the headlamp generated by laser diode, which allow you to see further, and is a safer light source to integrate or to install into the car headlamp. But in US, because of the FDA approval and all that, it's still not approved, the use of laser light. So laser, we know that is coherent light source, and LED is incoherent. And what is in between? In between, if you want to compromise, then you have to go into a new class of light source called super luminescent diode, or we call it SLD. SLD has a low temporal coherence, and the line width, the emission line width is in between laser and LED. It is operated at the regime of amplified spontaneous emissions. So unlike the spontaneous emissions from the LED and laser is stimulated emissions. Doing so, we'll be able to tap onto the large bandwidth, well, relatively large bandwidth, up to gigahertz or so, and it's droop free. And also, unlike laser lighting, you have a lot of high speckle density, but in this case, since it is low coherency, you'll be able to have, you do not have any speckle observed from this light source. We are not the first to look into the superluminescent diodes. Early day, up 10 years ago, Novagun, which is a company in Switzerland, they already venture into this field. They get about 100 milliwatt of power and being able to get a bandwidth. Bandwidth here, BW, is actually stand for the line width. How good is the coherency? EPFL also look into it quite a bit. But the general problem is the line width is relatively narrow, and also the power is quite low because the slope efficiency is quite low in this class of device. Then currently in the past 4 or 5 years or so, people has been trying to improve the optical power up to about 300 milliwatt or so. That is from Exelos. That's another company based in Switzerland. And currently, excuse me, currently New Mexico, the group in New Mexico, they demonstrate, although it's still with a decent power 100 milliwatt, they demonstrated a bandwidth, modulation bandwidth of up to 2.5 gigahertz in their current report. In our case, we design our SLB in a slightly different way. We use tilted angle. We demonstrate in tilted angle, and also using a gain media integrated with absorber to suppress the lasing oscillation. I'd like to point this out to you. This is the LED spectrum, which is very broad, and the narrow one, the stimulated emissions from the laser, and SLD is laying somewhere in between. Excuse me. We are the first group to have enough power from our SLD to integrate onto white color into to generate white color light source. Report those things in about 4 years ago, and we managed to also get the dual functions lighting and also the modulations up to about 800 something megahertz. Hundreds of milliwatt of power is still not too sufficient. So 2 years ago, we managed to increase the power to the record level above 300 milliwatt or so, close to 500 milliwatts, and yet being able to modulate the device at the above 1 gigabit per second and give decent CRI of about 81. And currently, we integrate the perovskite nanostructures into our lighting system and to get it up to about 90 or so 88 CRI, and yet give us a modulation speed of up to 1 gigabit per second. Another class of devices that we are high-speed devices that we are looking at is the DFB laser. Fabricating the DFB laser on indium nitrates or trinitrates material is highly challenging because it's a very tough material to etch and to pattern those grating onto it. Various different group has been trying different methods and not very successful, because by etching the gallium nitride introduce a lot of defect and also make the entire fabrications process highly complicated and very difficult. In our case, we use a slightly different method of creating or generating grating at the side wall, illustrated here. Until today, most of the, before this paper published in 2019 by our group, most of the work is done in blue color laser diodes. But in our case, we push it to green color. This is the first work, first DFB laser in green color. So the fabrications, we essentially make the grating at the side to control the wavelength. Although the order of grating is very low, we have to use a longer length, but be able to get a very nice single line frequency, single line lasing actions from this device and give decent power as well, 14 milliwatt of power at 513. Line width is really narrow, 31 picometer or so, and with a very, very good side-mode suppression ratio of more than 37 dB. Well, we designed this particular laser for two objectives or two applications. One is, of course, for high-speed modulations, for visible light communications. In sun spectrums, you have some missing line that we call it as a Fraunhofer line. So by sending signal in this missing spectrum or missing wavelength, we essentially we have very, very low background noise. And around 514 nanometers or so is one of the Fraunhofer line. That's why I designed this way. And another objective is to hit 420 something, 470 something nanometers, so that be able to do two things. One is the communication, that is another Fraunhofer line, and the other one is for strontium ion trapping, that is for atomic clock. This case, we demonstrated the DFB by using similar method, the sidewall grating, to get into a very high quality DFB laser with about the same power, tens of milliwatts, and are modulated by integrating into the VLC system using the 16 QAM OFDM, we managed to get beyond 10 gigabit per second. So 10 gigabit per second from a single diode, especially from laser diode, is one of the record as of today. Let's switch gear, talk about the receiver. Receiver, we know that for photodetector for VLC, we can have several options. PMT, somewhat bulky, but you'll be able to cover very large range of wavelength from about 200 nanometers UV all the way to near IR in 1500 nanometers or so. Another one is the low cost, it's like relatively low cost, silicon photodetector and the APD on silicon. Also being able to cover from 200 something, go all the way to what would not be that long wavelength of near infrared, but at the far red also. And another option will be developing high-speed photodetector for visible light communications by using 3 nitrides. This view graph shows the silicon photodetector, the APD. APD, since it is silicon material, and we always have the peak responsivity happen at the between 600 to 800 or so, depending on the coating and depending on the design. But one thing I'd like to point out is that it always gives very, very low responsivity at the UV region. And aluminum gallium nitride based MSN has been developed to focus to address the low responsivity of the silicon APD in UV wavelength. In our labs, we work on micro photodetector for these applications. If you want to have high speed, we know that the size of the component has to be small. But if it's small, it's quite difficult to align. So what we are doing here is to have an array of micro PD so that be able to increase the detections area and yet being able to keep it to very high speed. What you're seeing here is we are designing from the wafer level up to the component level and integrate onto the package. What we achieve today is a few for 2 wavelength. The 4 or 5 nanometers, we have been getting a few gigabit per second, 3.2 gigabit per second or so. We also work on the UV and violet PD that give us a few tens of megabit per second. Some of the high-speed, a new type of high-speed photodetector. This is something that we're quite proud of and like to point out in the UVC. There's no such thing called high-speed UVC photodetector as of today. That's cover the wavelength of 200 nanometers to 280 nanometers or so. This class of photodetector is very important for non-narrow sight or the solar blind communications applications. Again, when we look at the standard silicon photodetector, the off-the-shelf silicon photodetector, the responsivity of the detector at the UV region is very, very low. We're very much talking about 0.0 something amp per watt. And to increase the responsivity for such, for those low-cost APD, silicon-based APD, or the silicon photodetector, we use a color conversions method by using perovskite. Perovskite, when excited by perovskite material, when excited by UV light, you will get a green color emissions. So essentially, being able to convert the light in very high speed through the perovskite into green color light would be able to increase the responsivity of the detector by 4-fold. That reduce the cost and also allow us to operate our APD, the silicon-based APD, at very, very high speed. We know about the speed, the response time for our perovskite material, it has to be in gigabit per second, as we demonstrated in our laser-based solid-state lighting and VLC system. And in this study, we get about 34 megabit per second. The speed is not limited by our perovskite material, but it's limited by the light source that is available to us. As of today, we can only get a decent speed UVC LED at 278 nanometers. That very much gives us a few megabit megahertz of bandwidth to get into this bit rates. Currently, we also use make another type of photodetector, the micro PD array on at 405 nanometers for VLC applications. And in this case, we use a simple OK to get to 1.5 gigabit per second. This paper had just appeared in APEX not long ago. Right, let me draw the conclusions. We talk about the high-speed transmitter development for VLC, and also talk about the receiver, mainly talk about the receiver, micro PD, and new way of fabricating the UVC high-speed photodetector. With this, I would like to end by thank you my collaborators, my funding agency, and thank you all for your attentions.